Hi there! Pimoroni recently released the enviro-plus board for Raspberry Pis. It incorporates a couple of interesting sensors, and you can get it with a sensor for counting particulate matter in the air, which I had never come across before. So I ordered a set, and this video is the start of a review of this board. It is not a complete review because the sensors are complex, the datasheets are more like books, and I found a lot of issues with both the hardware and software of the enviro-plus, all of which took a long time to investigate. Everything came in 3 plastic bags. 3 because I had ordered the enviro-plus board, the particulate matter sensor, and a new Raspberry Pi Zero because I had none of the newer models with built-in Wi-Fi left. After unwrapping, we have the enviro-plus board, the particulate matter sensor, which is a little box, with fan outlet and 4 inlet holes, and of course the Raspberry Pi Zero, which I ordered without soldered-in connectors for a reason which will I explain shortly. A quick inspection of the enviro-plus. The big black rectangle is the 0.96-inch color LCD, 160 by 80 pixels with a protective film. Below we see the MIX 6814 gas sensor. The PM sign points to the back where the cable for the particulate matter sensor is supposed to be plugged in. The noise sign is the opening to a queued MEMS microphone. Then we have the ADS1015 analog to digital converter or ADC, and the LTR559 light and proximity sensor. And finally on the left side the BME280 temperature, pressure and humidity sensor. The board has some cutouts to minimize influences from the rest of the board on this rather sensitive device. The whole board is covered in white solder mask with some fancy scenery print, which unfortunately makes reverse engineering of the tracks very difficult. On the reverse we have at the bottom the connector for the PM sensor, and next to it on the right the square box is the MEMS microphone. Above the PM connector is the flex board to the LCD. The big black bar on top is the 40-pin connector for the Raspberry Pi GPIO. There are a handful of resistors, capacitors and 3 pin devices, probably transistors or FET, and that's about it. I am using this old Raspberry Pi Zero to show how the enviro-plus board is designed to be connected. You simply plug it into the GPIO, and you end up with a very compact sandwich like this. The only problem is that the Raspberry Pi gets hot, and with the enviro-plus and all its sensors, in particular the BME280 hovering less than 10 mm above it, this causes problems. I read that the Pimoroni software can compensate for that by reading the CPU temperature and using it to compensate the sensors, but I don't think this is an accurate solution. There are better ways to avoid or at least minimize the problem in the first place. The first is to increase the distance between the enviro-plus board and the Raspberry Pi. Use an extender like this one. The second way, which is what I choose, is to use an angled connector, which keeps the enviro-plus board well clear from the Raspberry Pi. The software installation is straightforward as described in the Pimoroni website. Besides the drivers for the sensors, you get a few examples. This is the all-in-one example, which displays sensor data on the LCD. Clearly the temperature reading is nonsense in my case, because the compensation for the CPU temperature assumes the board is sandwiched on top of the Raspberry Pi. Instead of fixing the relative complex all-in-one program, I used another example that just presents the BME280 values directly from the sensor on a terminal without CPU temperature-based compensation. The temperature reading was now consistently about 4 degrees too high. It should be around 26.3. Yes, we had a bit of a heat wave in the UK. To see if airflow changed the readings, I rigged a computer fan, which you see in the foreground, blowing at the BME280 sensor. The 12-volt fan was operating at only 5 volts, so the airflow was very gentle and just noticeable when holding a hand in front of the board. As you can see, with the fan, the sensor produced a much more sensible reading, which is only about 0.5 degrees too high. I turned the fan back off, and as you can see in this time-lapse video, over the course of several minutes, the readings went steadily back to above 30 degrees, despite the ambient temperature still being around 26.3. What's going on here? Let's have a closer look at the datasheet of the BME280. Its applications list GPS enhancement and indoor navigation because it's so sensitive that the air pressure reading can be used to detect floor changes or elevator use. But the traditional weather forecast is also listed, and the sensitivity and multi-use make this sensor very interesting. The pressure readings are quite accurate, plus minus 1 hectopascal. Incidentally, 100 pascals or 1 hectopascal or 1 HPA is the same as 1 millibar. The sensitivity and noise level depend on the oversampling and filtering, but can be as good as detecting a height change of about 1.7 centimeters. The temperature reading, on the other hand, isn't exciting. In the interesting range of 0 to 65 degrees, its absolute accuracy is just plus minus 1 degree Celsius, but its relative resolution is 0.01 degree. The reason for this is explained in the textbooks here, explaining that the primary purpose of the temperature sensor is to provide temperature compensation for pressure and humidity measurements. It can be used for estimation of ambient temperature, so we are only estimating and not measuring temperature. Furthermore, the footnotes explain that the temperature depends on a lot of things, and that includes self-heating, and it acknowledges that the readings would be typically above the ambient temperature. The self-heating effect explains that a gentle breeze over the sensor brings the temperature reading down to well within 1% of the actual value, and leaving it in still air makes it climb back 4 degrees above ambient. Can we remove or reduce self-heating? As you can see from the datasheet, the BME280 has extensive power management to the point of having 2 power feeds, one for the sensor part and one for the digital interface. This would allow turning the sensor power off in between measurements, but on the enviro-plus this is not possible. The next best thing are the 3 sensor modes: sleep, forced and normal. In forced mode, you need to explicitly ask the chip to do one set of measurements, and then it goes back to sleep until you ask for the next set of data, which could be minutes or hours later. In normal mode, the chip wakes up periodically to do a set of measurements and then goes back to sleep. The sleep time or standby time here can be selected in normal mode between 0.5 milliseconds and 1 second in 8 steps. The complexity of the sensor prompted the manufacturer to add a section on recommended modes. For environmental measurements, weather monitoring would be the most appropriate mode of operation. You can see this is targeted to produce the least power consumption, operating in forced mode with just one measurement every 60 seconds and no oversampling or filter. One last thing before leaving the datasheet, which is really more of a book and not a sheet at all. The reason why the BME280 can give you reasonably accurate pressure and humidity values is that after manufacturing, a whole set of calibrations are performed in the factory, and the necessary correction values, called trimming parameters, are stored in non-volatile memory on the chip. As a consequence of this, reading the data and making sense of it is not straightforward. Depending on the software capabilities, you can use an API provided by BOSCH, or alternatively, the datasheet contains several pages of C code that show how the trimming values are to be used to get the correct sensor values. This here is the code if you are using double precision floating point, which is what Python uses and what Pimoroni have implemented in their driver. I do want to point out one crucial thing. You can see that the first step, the corrected temperature, in some internal format is calculated as T-fine. This is then used in the calculations for pressure and humidity. This causes a problem. If the temperature is wrong, be it from radiated heat of a close-by Raspberry Pi or because of sensor self-heating, is the pressure and humidity also wrong? It kind of depends on how the chip works internally. If the temperature value is to compensate for effects on pressure and humidity circuitry inside the chip, then using the too high value is the right thing to do because it represents the chip's internal temperature. However, if the temperature is meant to represent ambient air temperature, then the pressure and humidity values will be wrong. Moreover, assuming you have a correction value to bring the BME280 temperature reading in line with the ambient temperature, then any correction value must be applied to T-fine before it goes into the calculation for pressure and humidity, and not just to the displayed temperature value as Pimoroni have done in their example code. I have contacted BOSCH Sensortec, the makers of the BME280, and asked that question, but not yet received a reply. In any case, I had to change the Pimoroni BME280 driver because I did not like how they implemented forced mode, and so I added the capability to correct the temperature for pressure and humidity calculation as well. As always, the code's on my GitHub page. Forced or normal mode is selected in the setup function, and I have no problem with that. The selected mode is programmed into the chip and stored in the class variable _mode. The problem comes in the get temperature or get pressure or get humidity functions that each call update sensor before returning temperature, pressure and humidity from stored global variables. Update sensor does check for forced mode and if necessary triggers a new reading. It then stores the red values in global variables. Originally, update sensor did not return anything by itself. You can see the problem here. To read just one set of temperature, pressure or humidity data in forced mode, you would trigger update sensor calls, causing 3 forced readings of the 3 values. That's 9 measurements in total, of which you throw away 6. The simple remedy is to make update sensor return all 3 measurements and never call any of those get functions. The other change is first a new function to set ambient temperature, which expects the correct value from ambient air temperature. This then in turn is passed to a new subclass function called correct temperature. That in turn uses the value to calculate the offset to the internal temperature as reported by the BME280. The offset is then used in the compensate temperature function to produce a corrected temperature fine value. So where to get the ambient temperature from? Luckily I had a few TMP36 sensors still lying around. These look like transistors and need just power and ground and produce a voltage that's proportionate to the temperature. In case of the TMP36, it has an offset of 500 millivolts and a scale of 10 millivolts per degree. So at 25 degrees you measure 750 millivolts output. First subtract 500 millivolts to get 250 and then divide by 10 to get 25.0 degrees Celsius. 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 25.0 degrees Cel The enviro-plus has a place for a 9-pin connector with a pin out shown here. It's very easy to add the TMP36 with 3 wires and read the temperature through the 4th unused channel of the ADC. The other 3 channels are used for the MIG6814 gas sensor, which we'll examine next. The MIG6814 sensor package has 3 metal oxide layers that are heated by separate heater elements. When chemicals are absorbed, the electrical conductivity changes locally, leading to a change of its electrical resistance. Analyzing the modifications of the resistance over time compared with reference values can give some information about gas concentrations. Of the 3 sensors in the MIG6814, the first one, named OX, is sensitive to oxidizing gases. The second one, red, senses reducing gases, and the third one, called NH3, senses ammonia. This is how the datasheet recommends using the sensor. The heating circuit is powered by 5 volts and uses resistors for current limiting. The recommended heater currents and power are shown in this table. The right diagram shows the recommended way to measure the resistance of the sensor layers. This is just for one sensor, RS, in this diagram. The point is that the resistance can change over several magnitudes, from say 1 kilo ohm to 2 mega ohms, which is very difficult to measure accuracy using a single range ADC. The recommended circuit would allow a microcontroller to select different reference resistors and thus adjusting the range for high or low ohm measurements, giving greater accuracy. The recommended heater schematic is a bit weird, and to make it clearer I redrew it here without the sensor part. 2 heaters are actually in series, but there is this additional resistor here that increases the current to the second heater ever so slightly. I guess this circuit was designed to reduce the overall power consumption by avoiding a large voltage drop across the current limiting resistor. The drawback is that this only works from 5 volts, and I don't think that is what the enviro-plus board uses. Unfortunately, Pimoroni does not publish schematics of their board, and the white soldering mask and double layer board makes tracing the PCB very difficult and time consuming. Well, certainly more time than I was willing to invest. The RPI does provide 5 volts, but the resistors on the back of the enviro-plus board have no resemblance with the recommended heating diagram on the left. In addition, on the enviro-plus, the heating is controlled by pin 24 of the GPIO, and since the heating current is too much for a GPIO output, the board certainly contains some 3-pin devices, which might be transistors or FETs, to turn the heating circuit on or off. Let's look at the way the circuit to measure the resistance is designed. Again, there is no official schematics, but the 356K resistors are easy to spot, and the software calculations in the example code confirm it. Notice the absence of the range switching circuitry recommended in the datasheet. Instead, each of the 3 ADC channels is directly measuring the voltage drop across a sensor fed from a 56K reference resistor. As I explained, for when hooking up an external temperature sensor by trial and error, I found that the 4th ADC channel is available on the pin ADC, and I suspect that the pin A3V3 is a separate reference voltage for ADC measurements. It certainly has a slightly different value from the 3.3 volts provided by the Raspberry Pi. So how does measuring the sensor resistance work? The ratio of the voltage across the reference resistor and the voltage across the sensor resistors are always the same as the ratio of the resistor values themselves. This is just a simple voltage divider. That means we can rearrange the equation to solve for Rx, the unknown resistance of the sensor. Uref can be expressed as the difference between the supply voltage U and Ux, the voltage drop across Rs. Substituting Uref That way we get this equation for Rx, and putting the known values in, we see that all we need is the value of Ux, which the ADC provides. If you examine the snippet of code here from the example program, you see that is exactly how they calculate the OX, red and NH3 values. OX, for example, is the first ADC voltage across the OX center and then converted to a resistance value. Slightly weird is setting the ADC gain to 6.148. First of all, that is an error because it should be 6.144. And I'm not sure what the driver makes of that. It certainly doesn't raise an error as it should. Secondly, given that the maximum voltage we will measure is just 3.3 volts, selecting 6.144 for full range means you have thrown away more than half of the available resolution. This little spreadsheet illustrates the problem. On the left we have the supply voltage with 3.3 volts and the reference resistor 56K, and a list of sample sensor resistance values which we may encounter, in this case a range from 1000 ohm to 2 meg ohm. The next column shows the current flowing through the sensor resistor, which drops from about 58 microamps to 1.6 microamps as the sensor resistor values get larger. The voltage drop across the sensor, our Ux on the other hand, works the other way. It's just 58 millivolts for low sense resistance values and exceeds 3.2 volts at the other end. Then we have the 4 sections, each representing one gain value. For the 6.14 volts gain, the least significant bit is 3 millivolts. Since we know the current in column B, we can convert the 3 millivolts LSB into an equivalent resistance. So for example, at a sense resistance of 1000 ohm, 3 millivolts represents an uncertainty of 51.8 ohm or up to 5.18% error. On the other end of the scale, the 2 meg ohm, 3 millivolt LSB represents an uncertainty of almost 2K, but only a tiny 0.09% error compared to the sense resistor. Doing the same calculation for the other ranges, we can see that the error gets less the lower the gain, but of course the 2.048 range and the 1.024 range can't be used for higher sense resistances because the voltage drop would exceed the range and cause an overflow. So we should really select a lower gain setting and in effect implement the auto ranging the datasheet originally suggested. But there's a catch, which probably explains why Pimoroni uses only the highest range and nothing else, and that is the input resistance of the ADC. The table here shows the input resistance in single-ended mode for different gains. The highest at 6.144 volts has 10 meg ohms, which drops to 6 for 4.086 and 2.048 and to just 3 meg ohms for 1.024 volts. Judging from the differential mode, the value of 100, by the way, should be 100K and not 100 meg ohm. This is an error in the datasheet. Input resistances of 3, 6 and even 10 meg ohm are in the same order as the higher sense resistance values, and they cannot be ignored. Luckily, that isn't too difficult. Our previous formula for calculating the sense resistance remains valid, except that resistance is actually the result of the real sensor resistance and the ADC input resistance connected in parallel. Given that we know how to calculate Rx and we know Ri from the datasheet, it is easy to calculate Rs. This code snippet of my solution is shown here. First of all, the read ADC function implements an auto ranging by testing for 4.096 volts first, and if the voltage is low enough, it changes the gain to either 2.048 or 1.024 and reads again. The weird channel name stuff is caused by the way the Pimoroni driver is implemented. In this box here you see how the previous formula for calculating the resistance, read MOS old, is now changed to compensate for the internal resistance of the ADC. So now that we can measure the sensor resistance reasonably accurately, what are we actually measuring? The Mix 6814 provides these three diagrams for the three sensors. The logarithmic x-axis shows the concentrations in parts per million, or ppm. The y-axis is also logarithmic and shows the ratio of the sense resistance Rs against the reference resistance R0. You can see immediately two large problems. First, while we now have Rs, we have no idea about R0, which we need to calculate the ratio to look up the ppm values. I collected some facts for these sensors on the right here. R0 is simply Rs measured at the right conditions. So all we need to do is find clean synthetic air of the right temperature and humidity. Good luck with that. I know that you can buy some boards with this sensor on, where the manufacturer tests each board in clean air, measures the R0s and provide the values with the boards. But sadly not here. The large manufacturing spread also means you can't reuse R0s measured for some other sensor. Each sensor needs its own calibration. The only method I can see at the moment is to do a long-term measurement, periodically recording Rs values and then checking that these produce a fairly constant average, which would then be a relative R0 for your chosen location, and naturally you would try to do this at a place and time where you would hope the air is as clean as possible. Thankfully, because all gases for which the NH3 and red sensors are sensitive are sloping down. This means the higher the NH3 and red resistance is, the cleaner the air, and this works without needing a ratio or R0. If we ignore nitrogen monoxide and hydrogen for the moment, the OX sensor characteristics for nitrogen dioxide is the other way. So that means the lower the OX sensor resistance, the less NO2 is in it. But the fact remains, without a true R0, converting resistance into ppm readouts is very problematic. Moreover, the sensors are somewhat influenced by humidity and massively by airflow, and should be placed behind a Teflon filter membrane. They could also be easily ruined by some solder flux vapors. We can just hope that when the enviro-plus board was assembled in China, these precautions were followed. Assuming you selected an R0 which wasn't quite right, what would the effect be? Let's look at the example of the red sensor and carbon monoxide. If we assume that for my sensor the correct R0 for red would be 10,000 ohm, for example, then if we measure 10,000 ohm, we get a ratio of 1, which according to the diagram corresponds to a CO concentration of 4.37 ppm. Similar, if the resistance dropped to 8,000 ohm, the ratio is now 0.8, and that indicates that the CO concentration has increased to 5.7 ppm. And at 1000 ohm we get 67.3 ppm. So far so good. But what if, despite all our efforts of finding the cleanest air around, we picked a location and time that already had 5.7 ppm of CO? The sensor would have shown 8000 ohm, and we would have selected that as our R0 and show a concentration of a ratio of 1 of 4.37 instead of 5.7, which would be the correct value. Similar, a drop to 1000 ohms would now be a ratio of 0.125 instead of 0.1, and subsequently we would now show a reading of 51.6 instead of 67.3. That might not sound too dramatically wrong, but because of the logarithmic scale, the error gets quickly larger the further away we get from 1. So the fact is, we can confidently detect if air gets better or worse, and we may tie alerts to sudden drops on air quality, but absolute readouts are probably not a good idea on the enviro-plus boards. There's also the problem that the sensor responds to many different gases that could all be in the air to some proportion. You see, for a given ratio, there are sometimes many possible gases that could be responsible, and there's no way of telling which. However, if despite all that you want to convert a ratio into ppm, let me show you how to do this. You need to carefully enlarge and examine the diagram to collect a few points for each graph, like the coordinates of the endpoints and at least one point in between. With coordinates I mean pairs of y-axis, and that's the ratio, and x-axis, the ppm. Then for each gas you put the readings into a spreadsheet. Like for H2S here, I just collected 3 pairs, but ammonia was far easier to read, so I collected 5 pairs, and so on for all the other gases in this diagram. Then separately for each gas you select the collected pairs and run a regression analysis over it. Excel has this, and so has LibreOffice Calc, which I'm using here. You need to select the power regression option because the graphs are flat lines, but only when plotted logarithmically. The output is what you see on the right for each gas, and as I just copied here again. The regression test comes up with the parameters for an exponential function that fits the data, the sample points, and then provides a copy using the given ratios and calculates the output. So for H2S, you see that for a ratio of 0.65, I was reading 0.1 ppm, and the regression module produces 0.097. All in all, the H2S model is maybe an adequate but not a very good fit because the graph is so difficult to read. It's also shown by the R-square value, showing only 0.985 as a measure how well this model fits. You want this value to get as close as possible to 1 and the standard error as small as possible. You see, for other gases I managed to get a better fitting model. Let's have a closer look at the model for carbon monoxide. You see that each calculation is based on the ratio first raised to the power shown in slope and then multiplied by the value in intercept. I did not come up with this. It's all automatically calculated and inserted for you by the regression analysis function of the spreadsheet when you point to the 6 sample points here. I copied this magic formula to the right here and changed it to take the ratio value from cell E67. You see, I can now type in any ratio I want and get the associated ppm value. 0.8 gives us 5.7. 0.8, for example, is a 0.37. 0.001. Wow. Oh boy, we are in trouble. Don't breathe in. But seriously, it's of course nonsense to use ratios that are outside the range defined in the diagram itself. As the last sensor covered in this review, I want to talk about the particulate matter or PM sensor. The PMS5003 is made in Beijing by Plant Tower Technology. It operates on the principle of Mie scattering, that is, what happens if an electromagnetic wave, in this case light, meets particles that have a diameter in the order of the wavelength. For particles in the range of 0.3 micrometers to 10 micrometers, we are talking about borderline ultraviolet all the way to infrared. In this case, laser light is used as a source and a scatter effect, like spreading the beam, is detected in the cavity. This is measured and then converted into an output. The manual warns of trying to open the sensor housing, and for the time being I'm more interested in the results than how it works internally. I'm just wondering if they use 3 different lasers, because the particle size range is quite wide, and I wonder if light with just one wavelength would produce sufficient scattering for all sizes. 3 different lasers would also explain the 3 ranges shown here in the datasheet. The PMS5003 produces 12 outputs at each measurement cycle, roughly every 2.5 seconds. The yellow section is the actual measured data. It's the count of particles that size per 0.1 liters of air. These counts are then converted to the standardized PM1.0, PM2.5 and PM10 values, which have the unit of microgram per cubic meter. To get from particle count to grams, the conversion uses either a standardized industrial metal particle or some standardized atmospheric air pollution particle. Hence, the sensor produces 2 sets of PM1.0, 2.5 and 10 values, and you can choose which is more representative of the environment you are measuring in. PM10 and PM2.5 size particles are quite dangerous for your health, and there are limits how much of these pollutants are allowed. For the EU, for example, the yearly average for PM10 is 40 and for PM2.5 is 25. The daily average for PM10 is 50, with up to 35 exceedances per year allowed. While it is great to have an affordable way of checking the pollution in your house, a word of caution: the datasheet shows that PM2.5 has an error rate of plus minus 10 micrograms per cubic meter. So if we are reading a value like 15, it may actually be only 5, but it could also be 25, which is the EU limit for the PM2.5 average per year. The other thing worth mentioning is the MTTF, or mean time to fail, which is 3 years or greater. So on average, your sensor will be dead after about 3 years of continuous operation. The connection to the computer is using a serial protocol with 3.3 volts level at 9600 bits per second. Don't use 5 volts, the only 5 volts is the power to the fan. The message format is well documented in the datasheet and straightforward. The way Pimoroni implemented this is that the serial port used is TTY-AMA0, and the set control and reset control are driven by pins 22 and pin 27 of the GPIO. For compatibility, it would be better if the driver used TTI serial 0, because on later Raspberry Pis, TTY-AMA0 may connect to Bluetooth instead. Set is actually just an enable signal. If pulled low, the PMS5003 goes into sleep mode. If reset is pulled momentarily low, the PMS5003 resets. With respect to installation requirements, the datasheet states that it's designed for indoor use, and additional protection is needed for use in kitchens, water mist conditions like bathrooms, outdoors, or places with very high concentration of pollutants. To test all this, I wrote my own little test program, which you can download from my Github page. It uses the Pimoroni drivers except for the BME280 because of the problems with the forced mode and the temperature correction. I'm using the fourth ADC channel to read the TMP36 sensor and then correct the BME280 temperature in every cycle. The three gas sensors in the MIG6814 are read using the ADC auto ranging and correct for the internal resistance of the ADC at each gain setting. Besides the printout on the terminal, the program also produces a time-stamped recording in CSV format. The test setup has the enviro-plus mounted to its Raspberry Pi with the particulate sensor attached and the extra temperature sensor connected. The fan in the foreground is for the first experiment but not running at the moment. At the start, the program records how much the BME280 temperature differs from the external sensor, and from now on the BME280 temperature is corrected to match the temperature of the external sensor at every refresh. The refresh rate of the screen is 10 seconds, and to speed things up I'm playing this recording as a time-lapse video. The gas sensor heater need at least a minute to get to temperature, and so the reported resistance values are not stable yet. When I ran these tests, I did not realize that the 10-second refresh somehow clashes with the way Pimoroni has designed their PMS5003 driver, and so there is a 2-minute delay before particle size data is returned by the driver. The sensor itself responds within 10 seconds or so. I have yet to deep dive into the PMS5003 driver to fix this. By the looks of it, they expect the read function to be called more often than the sensor sending data, which is every 2.5 seconds. The data is updated anyway, so for now ignore this initial delay. In the first experiment, I want to show what happens if you expose the enviro-plus board to even a gentle breeze. The breeze is simulated by the 12-volt fan running at just 5 volts. You can just feel the air move at the enviro-plus. Even only moderate wind should be much stronger. For this experiment, I disabled the correction of the BME280 temperature by the external sensor. You can see the effect on the NH3 value and the temperature reading. Turning the fan off again and things start to go back to the previous values. Since the program recorded all the measurements, it is easy to create a plot of what happened. TMP2 is the external temperature sensor and TMP is the temperature reported by the BME280. You can see that the BME280 temperature, which was still creeping up, takes a nosedive when the fan is turned on because the airflow is cooling the chip. For the same reason, you can see that the NH3 sensor is going crazy because its heater can't keep up with the cooling of its chip. So by putting both sensors on the same board, the enviro-plus designers really created a bit of a headache. We would like to have the BME280 chip exposed to some airflow, but we definitely do not want the airflow to reach the MIG6814 chip. Probably the best solution is to mount the board in an enclosure in such a way that the MIG6814 is behind a Teflon window and protected from being hit directly by airflow, and put some breathing holes above the BME280. That will cause wrong temperature readings by the BME280, but an external temperature sensor can fix that. For the next test, I removed the fan and restored the correction of the BME280 temperature by the external sensor. I hunted around in the household to find something that contained ammonia and found this toilet bowl cleaner. Let's see what happens when the enviro-plus gets a whiff of toilet duck. It's not very easy to see on the terminal, but we also have the recording which we can plot. There's definitely a response on all three sensors. The NH3 reaction is the most pronounced, as expected, but the red sensor and even the ox sensor also show an effect. It makes sense that the red sensor and the NH3 sensor both responded, because as you can see, both are sensitive to ammonia. I don't know why the ox sensor responded. I would not have expected nitrogen monoxide, nitrogen dioxide, or hydrogen coming out of a toilet bowl cleaner, but who knows what they put in these things these days. Maybe we just discovered that the ox sensor is reacting to the pine scent. For this test I'm using concentrated ethanol. Actually, this stuff is only about 90% ethanol and the rest is made up by methanol and some dye. In the UK this is called methylated spirit and mostly used for cleaning windows. Wow, there's definitely some big response here. The resistances are all dropping into the cellar, it appears. The plot confirms there's a strong reaction. Again, all three sensors responded, with the most pronounced effect from the NH3 sensor, which basically went into free fall. As before, it makes sense that both the NH3 and the red sensor responded, as both are sensitive to ethanol. And as before, it's a mystery why the OX sensor responded. It can't be nitrogen monoxide, because that would increase the resistance, not lower it. So either nitrogen dioxide or hydrogen. For this last test I have changed the program in two ways. First, it prints the timestamp used in the recording in the first row. This makes it easier for me to correlate things I'm doing with the data in the recording. Secondly, the program is running much faster with a 1 second sleep time between cycles. This means we have a much higher resolution, but the faster refresh causes the occasional glitch in the video since I'm recording the terminal via a VNC connection. In hindsight, SSH would have been much better choice for this test. To test both the gas and particulate sensors together, I came up with this idea of using a candle. And when blowing it out, I purposely blow some of the smoke in the direction of the particulate sensor. While the room slowly fills with the typical paraffin smell when you blow out the candle, the particulate sensor definitely goes wild after some delay. The recording of this test promises to be very interesting. Okay, so here's the recording. Because the program was running 10 times faster than in the previous examples, the resolution is much better. It is interesting that the NH3 and the red gas sensors both registered the lighting and the extinction of the candle as dips, but while the candle was burning, the readings almost recovered to the original values. And after the candle was extinguished, the particulate sensor went nuts. The PM2.5 jumped to above 1500 micrograms per cubic meter and the PM10 to above 2000. So really unhealthy stuff, candle smoke. There seems to be also a small blip after I lightened the candle. To see more, I plotted the actual particle counts, which I recorded as well. This diagram shows the number of different sized particles in 0.1 liters of air. I think the 0.3 micrometer count is actually cut off and would be even higher, but the maximum value the sensor returns is 16-bit, so 65,535 is the highest number possible. There's definitely a small peak after I lit the candle, about the same time delay as the big response after I blew it out. So this could maybe the soot from the lighter flame. I definitely plan to do some more tests in the future. Well, this video is way too long already and I only covered 3 sensors. In future videos I will look at the light and proximity sensor, the microphone and the LCD itself, and of course do more tests. My conclusion so far: not providing R0s for the gas sensor and leaving it uncovered severely downgrades the utility of the enviro-plus for serious environmental analysis. Unless you add an external temperature sensor, you can also forget measuring temperature with any degree of accuracy. The saving grace is the particulate sensor, but to be fair, it isn't actually part of the enviro-plus. True, it's using the enviro-plus as a convenient way to connect it to a Raspberry Pi, but you have to buy it separately for £25, and if you make your own cable, you can easily get particulate data without needing an enviro-plus at all. So if you're tempted, there are quite a number of shortcomings you should consider. Also, add to this that Pimoroni does not document the hardware and their driver software is equally rather cryptic, especially for newcomers into Python. On the other hand, playing with the sensors, understanding the datasheets and changing the software was entertaining and for me very educational. So in that sense the enviro-plus provides good value, and let's face it, it would be rather boring if everything just worked. Thanks for watching.